Now, in this lecture, we find out the radius of the circle using two different methods. In the drawing, we have triangle ABC that blocks this circle, or the circle is inscribed by triangle ABC. In addition, we know that angle ABC, this angle equals to 60 degrees in its size. This angle ACB, equals to 75 degrees in its size. And we also know that side BC of this triangle ABC, equals to 2 units in its length. And again, our mission is to find out the radius of this circle. So we start with the first method, and we will do a construction. That is to say, from point C, we will draw perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C on AB as D. In the next step, we focus on the right triangle BDC. So I'll copy triangle BDC in the new page, and we will analyze this triangle BDC. So actually, this is triangle BDC that I copied from the original drawing. Angle DBC equals to 60 degrees in its size, and side BC on this triangle DBC equals to 2 units in its length. In this triangle BDC, cosine 60 degrees equals to BD over BC. So cosine 60 degrees equals to BD over BC. BC is 2. Cosine 60 degrees is 1/2. So 1/2 equals to BD over 2. Here we will multiply this equation by 2, and we get that BD equals to 2 units in its length. BD equals to 1. Here we multiply this equation by 2, so we get that BD equals to 1 unit in its length. This is side line segment BD that equals to 1 unit in its length. We'll continue to focus on the right triangle BDC. On the right triangle BDC, sinus 60 degrees equals to DC over BC. So sinus 60 degrees equals to DC over BC. BC is 2. Sinus 60 degrees is square root of 3 over 2. So square root of 3 over 2 equals to DC over 2. Here we'll multiply this equation by 2, and we get that DC equals to the square root of 3 units in its length. Okay, DC equals to the square root of 3 units. This 97 DC equals to the square root of 3 units in its length. In the right triangle BDC, this angle equals to 60 degrees, this angle equals to 90 degrees, 60 degrees plus 90 degrees is 150 degrees, therefore the missing angle here must be equal to 30 degrees in its size. Again, in order to complete the sum of the angles in this triangle BDC 280 degrees, the missing angle here must be equal to 30 degrees. So it is given us the equation that angle ACB equals to 75 degrees. So angle ACB minus angle DCB must be equal to the missing angle ACD. So angle ACD equals to 75 degrees minus 30 degrees, it is 45 degrees. So the missing angle ACD equals to 45 degrees in its size. So in the right triangle ADC, this angle equals to 45 degrees, this angle equals to 90 degrees. 90 degrees plus 45 degrees is 135 degrees. So the missing angle here must be also equal to 45 degrees in its size. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. So I will copy the right triangle ADC in the new page and we'll analyze this right triangle ADC. So actually, this is the right triangle ADC that I copied from the original drawing. Triangle ADC is a right triangle, and it is also an isosceles triangle because of the fact that those two angles are equal to each other. And we have the rule that in front of equal angles in the triangle there are equal sides. So in front of those two equal angles, we have those two sides that must be equal to each other. That is to say, side DC must be equal to side AD in this triangle ADC. But we have already found out that DC equals to the square root of 3 units. So here DC equals to the square root of 3 units, and from this equation we derive that AD must be also equal to the square root of 3 units in its length. AD equals to the square root of 3 units in its length. So we can write down in the original drawing that this side AD equals to the square root of 3 units in its length. We'll continue to focus on the right triangle ADC. On the right triangle ADC, by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in the right triangle ADC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC squared, that is the square of the hypotenuse, must be equal to AD squared plus DC squared. So AC squared, the square of the hypotenuse, equals to AD squared. AD is equal to 3, therefore AD squared is equal to 3 squared, that is 3, plus DC squared. DC is also square root of 3, therefore DC squared is equal to 3 squared, that is 3. So AC squared equals to 3 plus 3, that is 6. We take a root out of this equation and we get that AC equals to the square root of 6 units in its length. So here, this side AC equals to the square root of 6 units in its length. In the next step, I will present to you a new rule and we will implement the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is inscribed by triangle ABC is equals to R, the radius R equals to the area of triangle ABC that blocks the circle over S. S is the semi-perimeter of triangle ABC that blocks the circle. The semi-perimeter of any triangle equals to the perimeter, that is the sum of its side lengths, over 2. So you can see in the drawing, we have triangle ABC could be any triangle. Inside triangle ABC we have a circle that is blocked by this triangle, and according to rule number 15 we can find out the radius of this circle that is blocked by triangle ABC only by knowing the area of triangle ABC and the side lengths of the triangle. The radius R will be equal to the area of triangle ABC over the semi-perimeter of this triangle ABC. We can actually implement rule number 15 in our drawing. Why? Because in our drawing we have triangle ABC that blocks this circle, and we know that the side lengths of this triangle ABC, and the radius of this circle will be equal to the area of triangle ABC over the semi-perimeter of this triangle ABC. So I write it down. The radius of our circle, the radius that we are looking for, will be equal to the area of triangle ABC. The square brackets is the sign for the area, it means the area of triangle ABC over S, that is actually the semi-perimeter of triangle ABC. So the area of triangle ABC equals to the base of the triangle times the height to the base over 2. That is actually the area of any triangle. The base, the height must create 90 degrees with the base. The base times the height over 2 is the area of triangle ABC, divided by the semi-perimeter of this triangle ABC. The semi-perimeter is the perimeter over 2. The perimeter is AB plus BC plus AC. AB plus BC plus AC. If we divide it by 2, we'll get the semi-perimeter. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. And we left, after we have cancelled the 2, we left only with the base times the height over AB plus BC plus AC. We take the base of this triangle ABC, F side AB, times the height to the base. The height must create 90 degrees with the base AB. Here, 9 segment CD creates 90 degrees with the base AB, therefore the height is CD. Again, the height is CD divided with, so 2 is cancelled. And here we know that side AB equals to the square root of 3 plus 1. Side BC equals to 2 units in its length according to what is given us in the question. And side AC, we found out that side AC of this triangle ABC equals to the square root of 6 units in its length. Again, we have here AB. AB is equal to 3 plus 1 times CD. CD equals to the square root of 3 divided by square root of 3 plus 1 plus 2 plus square root of 6. So here, so the radius R equals to actually the area of triangle ABC equals to 2.366 square units divided by the semi-perimeter of the triangle, that is actually 3.591, and 2.366 over 3.591 equals to 0.6589 units. So if I found out that the radius of this circle that is inscribed by triangle ABC equals to 0.6589 units. Actually, the result of this expression, the value of this expression equals to R. Okay, and R equals to 0.6589 units. So the radius of this circle, the radius R, equals to 0.6589 units. So we finished with the first method. In the next step, I will present to you how to find out the radius of this circle that is inscribed by triangle ABC according to the second method. We define the center of this circle, this point is O. We define the point of tendency of tangent BC with this circle as D. We define the point of tendency of tangent AC with this circle as F. And we define the point of tendency of tangent AB with this circle as E. We will join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle. We define the radius of this circle as R, so OD equals to R. R is the radius that you are looking for in this question. And we have here rule number 1, according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have the drawing AB is tangent to this circle is point M is the point of tendency, and we have the radius OM that is drawn to point M, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to this rule, rule number 1. Actually, we can implement rule number 1 in our drawing. We have the radius OD of this circle that is drawn to point D, that is to say it is drawn to point D, that is the point of tendency of tangent BC with this circle. Whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius TO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. So here EO is the radius of this circle, therefore it is equals to R. According to the sum rule, rule number 1, we have the radius OE that is drawn to point E, therefore according to rule number 1, this angle will be equal to 90 degrees, and this angle will also equal to 90 degrees. We join points O and F together by a straight line. OF is the radius of this circle, that is to say it is equals to R. Again, the radius OF is drawn to point F, that is the point of tendency of tangent AC with this circle, and whenever we have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius FO. That is to say this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We have also rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. So in the drawing we have a circle, and we have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule number 2, they are equal to each other. That is to say, PA equals to PB. We can actually implement rule number 2 in our drawing. In our drawing, if we focus on the common external point, point C, from the common external point, point C, we have two tangents to this circle, tangent CF and tangent CD. According to rule number 2, they are equal to each other. That is to say, CF equals to CD. CF equals to CD according to rule number 2. Likewise, we will focus on the common external point, point B. From the common external point, point B, we have two tangents to this circle, tangent BD and tangent BE. And according to rule number 2, they are equal to each other. That is to say, BE equals to BD. BE equals to BD. According to the same rule, rule number 2. In the next step, we join points O and B together by a straight line. And we join points O and C together by a straight line. In the next step, we prove that the yellow right triangle EBO is congruent to the green right triangle OBD. So I write it down. We'll prove that the yellow right triangle EBO is congruent to the green right triangle ODB. So why those two right triangles congruent to each other? First of all, BE in the yellow triangle equals to side BD in the green triangle. Here BE equals to BD according to rule number 2. Repeat again. Side BE in the yellow triangle equals to side BD in the green triangle according to rule number 2. In addition, those two sides, they are both the radii of this circle, therefore they are equal to each other. So EO equals to OD. Repeat again. Side EO in the yellow triangle equals to side OD in the green triangle. They are both the radii of the circle, therefore they are equal to each other. And finally, side BO is a common side that belongs to both triangles, therefore you can write down that side BO equals to itself as a common side that belongs to both triangles. So BO equals to BO. Again, side BO equals to itself as a common side that belongs to both triangles. So we actually proved that all the three sides of the yellow triangle BEO are correspondingly equal to all the three sides of the green right triangle BOD. Therefore we proved that the yellow triangle EBO is congruent this is the sign of congruent to the green right triangle ODB, according to side rule. And from the fact that those two triangles can point to each other, we will derive that those two angles they are equal to each other. So this is angle EBO in the yellow triangle, and it is equals to this angle is actually angle OBD in the green triangle. Repeat again. Angle EBO in the yellow triangle equals to angle OBD in the green triangle, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if we define one angle is theta, then the other angle must be also equal to theta, because they are equal to each other. So this is angle theta plus angle theta, in total they must be equal to 60 degrees according to what is given us in the question. So 2 theta equals to 60 degrees. We divide this equation by 2 and we get that angle theta equals to 60 over 2, that is 30 degrees. So this is angle theta, that equals to 30 degrees in its size. In the next step, I'll copy the green right triangle OBD in the new page, and we'll analyze this green right triangle OBD. Actually, this is the green right triangle OBD that I copied from the original drawing. Here, tangents 30 degrees equals to OD over BD. So tangents 30 degrees equals to OD. OD is the radius of the circle. This is equals to R over BD. In conclusion, found out that tangents 30 degrees equals to R over BD. Here we will multiply this equation by BD and then we will divide it by tangents 30 degrees, and finally we will get that BD equals to R over tangents 30 degrees. Repeat again. We actually found out that BD equals to R over tangents 30 degrees, so I can write down in the original drawing. So this is side BD, that is equals to R over tangents 30 degrees. In the next step, we repeat on the same process on the pink triangle ODC, on the orange triangle ODC, and the pink triangle, triangle OFC. So first of all, we prove that the pink triangle is going that the orange triangle is going to the pink triangle. So the orange triangle is triangle ODC. And the pink triangle is triangle OFC. So why those two triangles can go into each other? First of all, CD equals to CF. Here, CD equals to CF according to rule number 2. Repeat again. CD in the orange triangle equals to CF in the pink triangle according to rule number 2. In addition, those two sides, side OD and side OF, they are both the radii of the circle, therefore they are equal to each other. So side OD in the orange triangle equals to side OF in the pink triangle. They are both the radii of the circle, therefore they are equal to each other. OD equals to OF. They are both the radii of the circle, therefore they are equal to each other. And finally, OC is a common side that belongs to both triangles, so we can write down that OC equals to itself as a common side that belongs to both triangles. So OC equals to itself as a common side that belongs to both triangles. So actually proved that all the three sides of the orange triangle ODC are correspondingly equal to all the three sides of the pink triangle OFC. Therefore, those two right triangles can go into each other according to side rule. So I write it down. Triangle, the pink triangle ODC is congruent. This is the sign of congruent to the right pink triangle OFC according to side rule. And for the fact that those two triangles can go into each other, we derive that those two angles, they are equal to each other. So this is angle DCO in the orange triangle, and it is equal to this angle that is actually angle OCF in the pink triangle. Repeat again, angle DCO in the orange triangle equals to angle OCF in the pink triangle, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if we define one angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. So, okay. So here alpha plus alpha equals to 75 degrees according to what is given us in the question. That is to say, 2 alpha equals to 75 degrees. Here we divide this equation by 2 and we get that Angle alpha equals to 37.5 degrees in its size. So actually this is angle alpha that is equals to 37.5 degrees. In the next step, I will copy the right orange triangle ODC in the new page and we'll analyze it. So actually this is the right triangle ODC, the right orange triangle ODC that I copied from the original domain. This right triangle ODC tangents 37.5 degrees equals to OD over DC. OD is the radius of the circle, therefore it is equals to R over DC. In conclusion, found out that tangents 37.5 degrees equals to R over DC. Here we will multiply this equation by DC and then we'll divide it by tangents 37.5 degrees and we get that DC equals to R over tangents 37.5 degrees. So actually I found out that this line segment DC equals to R over tangents 37.5 degrees. Okay. BC from the drawing it is very easy to see that BC equals to BD plus DC. Again, BC equals to BD plus DC. Repeat again, BC equals to BD plus DC. BC equals to 2 units according to what is given as the question, and it is equals to BD. We have already found out that BD equals to R over tangents 30 degrees plus DC. We just right now found out that DC equals to R over tangents 37.5 degrees. So in conclusion, we found out that 2 equals to R over tangents 30 degrees plus R over tangents 37.5 degrees. Here we take R as a common factor from those two expressions and we get that 2 equals to, so R was taken as a common factor. Inside the brackets we left here with 1 over tangents 30 degrees Here after we took r as a common factor, from this expression we left only with 1 over minus 37.5 degrees. So if we found out that 2 equals to r and 1 over minus 30 degrees equals to 1.732 plus 1 over minus 37.5 degrees equals to 1.3032. So in conclusion, we actually found out that two equals to r times 1.732 plus 1.3032. So 2 equals to r and 1.732 plus 1.3032, it is equals to 3.0352. We will divide this equation by 30352 and we get that r equals to 2 over 3.0352. 2 over 3.0352 equals to 0.6589 units. So actually found out that the radius of the circle, the radius that we are looking for, is equal to 0.6589 units. That is the answer to the question according to the second method. So in the next step, I will summarize the lecture. We'll start with the first method, of course. In this lecture, we found out the radius of this circle that is inscribed by triangle ABC, or triangle ABC blocks this circle. We know that angle ABC equals to 60 degrees in size, angle ACB equals to 75 degrees in size, and we also know that side DC equals to 2 units, and side BC equals to 2 units in its length. Again, our mission is to find out the radius of this circle that is inscribed by this triangle ABC. In the first method, we did a construction, that is to say from point C, we draw perpendicular on AB. That is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB is D. Then I copied the right triangle CDB in the new page and we analyze this right triangle CDB. This is the right triangle BDC that I copied from the original drawing. This angle equals to 60 degrees according to what we given the equation. This angle equals to 90 degrees according to our construction. And side BC equals to 2 units according to what is given as the equation. In the right triangle BDC, this right triangle BDC, cosine 60 degrees equals to BD over BC. So cosine 60 degrees equals to BD and BC is 2. So cosine 60 degrees in total equals to BD over 2. cosine 60 degrees is 1/2, so 1/2 equals to BD over 2. We multiply this equation by 2 and finally found out that BD equals to 1. BD, this is side BD, that equals to 1 unit in its length. Then we continue to focus on this right triangle, triangle BDC. On the right triangle BDC, sinus 60 degrees equals to DC over BC. Sinus 60 degrees equals to DC over BC. That is to say, sinus 60 degrees equals to DC over BC, and BC is 2. So sinus 60 degrees in total equals to DC over 2. Sinus 60 degrees is square root of 3 over 2. Therefore, square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2 and finally found out that side DC equals to the square root of 3 units. This is side DC, it is equal to the square root of 3 units in its length. Then, in the right triangle DBC, this angle equals to side 60 degrees, this angle equals to 90 degrees. 60 degrees plus 90 degrees, it is 150 degrees. Therefore, the missing angle here must be equal to 30 degrees. In order to complete the sum of the angles in this right triangle DCB 280 degrees, the missing angle here must be equal to 30 degrees. So it is given as the equation that angle ACB equals to 75 degrees. Here, angle ACB equals to 75 degrees in its size. Angle DCB equals to 30 degrees. Therefore, angle ACB minus angle DCB must be equal to the missing angle, that is actually angle ACD. That is to say, angle ACD equals to 75 degrees minus 30 degrees, it is 45 degrees. So angle ACD equals to 45 degrees in its size. So, in the right triangle ADC, this angle equals to 90 degrees, this angle equals to 45 degrees. 90 degrees plus 45 degrees, it is 135 degrees. Therefore, the missing angle here must be equal to 45 degrees. Again, in order to complete the sum of the angles in this right triangle ADC to 180 degrees, the missing angle here must be equal to 45 degrees. Then I copy the right triangle ADC in the new page and we analyze this right triangle ADC. This is the right triangle ADC, then I copy from the original drawing. We just right now found out that those two angles are both equal to 45 degrees. That is to say, triangle ADC, it is a right triangle and it is also an isosceles triangle. We have the rule that in front of equal angles in the triangle there are equal sides. So in front of those two equal angles, we have those two sides that must be also equal to each other. That is to say, side AD must be equal to side DC, because they are located in front of those two equal angles. So AD equals to DC, but we know that DC equals to square root of 3 units. And from this equation, square root of 3 equals to DC equals to AD, we derive that side AD also equals to the square root of 3 units in its length. Here, this is side AD, this equals to the square root of 3 units in its length. Okay. Then we continue to focus on the right and the associated triangle ADC. Here we implemented the Pythagoras theorem on this right and the associated triangle ADC. According to the Pythagoras theorem, AC square equals to AD square plus DC square. Again, AC square equals to AD square plus DC square. So AC square, that is the square of the hypotenuse, equals to AD square. AD is square root of 3, therefore AD square is square root of 3 square, that is 3, plus DC square. Again, DC is also square root of 3, therefore DC square is square root of 3 square, that is 3. So AC square in total equals to 3 plus 3, that is 6. We took out of the equation and finally found out that the length of side AC equals to the square root of 6 units. Here, this is side AC of triangle ABC, this is equal to square root of 6 units in its length. Okay. Then I presented to you rule number 15, and we implemented rule number 15 in our drawing. According to rule number 15, the radius of a circle that is inscribed by triangle ABC is equals to R, the radius R equals to the area of triangle ABC that blocks the circle over the semi-perimeter of triangle ABC. The semi-perimeter of any triangle is equals to the perimeter over 2. The perimeter is the sum of its sides lengths. And then if we divide the perimeter by 2, we get the semi-perimeter S. So here in the drawing we have a triangle ABC that could be any triangle. This triangle ABC blocks this circle. This circle is inscribed by triangle ABC. Again, the radius R of this circle equals to the area of triangle ABC over the semi-perimeter of this triangle ABC. Again, in the semi-perimeter is the perimeter over 2. The perimeter is AB plus BC plus AC, and if we divide it by 2, we get the semi-perimeter S. We actually can implement rule number 15 in our drawing. Why? Because in our drawing we have triangle ABC that blocks this circle, or this circle is inscribed by triangle ABC. Therefore, the radius of this circle that is inscribed by triangle ABC must be equal to the area of triangle ABC over the semi-perimeter of this triangle ABC. The radius R of the circle that is inscribed by triangle ABC equals to the area of triangle ABC over the semi-perimeter of this triangle ABC. Okay. The area of any triangle is the base of the triangle times the height of the base over 2, and the semi-perimeter of this triangle ABC equals to the perimeter over 2. The perimeter is AB plus BC plus AC, and if we divide the perimeter by 2, we get the semi-perimeter S. So in total, the semi-perimeter S of triangle ABC equals to AB plus BC plus AC over 2. Here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we have only with AB times CD equals to AB plus BC plus AC. AB is square root of 3 plus 1, BC is 2, and AC is square root of 6. Again, AB is square root of 3 plus 1, and here CD is square root of 3. So in conclusion, found out that the radius of this circle that is blocked, that is inscribed by triangle ABC equals to the square root of 3 plus 1 times square root of 3 over square root of 3 plus 1 plus 2 plus square root of 6. This, the value of this expression, in total it is equals to 0.6589 units. That is to say, we actually found out that the radius of this circle that is inscribed by this triangle ABC, the radius R equals to 0.6589 units. So we finished with the first method. Then I actually presented to you how to find out the radius of this circle according to the second method. In the second method, we define the center of this circle here as point O. Then we define the point of tendency of tangent AB with this circle as C. We define the point of tendency of tangent BC with this circle as D. And we define the point of tendency of tangent AC with this circle as F. Then we join points O and D together by straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle that is that we defined as R. That is the radius that we are looking for. We have the radius R that is drawn to point D. That is to say it is drawn to the point of tendency, that is actually point D. And whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Then we join points O and D together by straight line. O is the radius. The radius O is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees. We join points O and F. OF is the radius of the circle. The radius of this circle is drawn to point F, that is the point of tendency of tangent AC with this circle. And therefore, according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Then, according, we have also rule number 2 that we can implement here. If we focus on the common standpoint, point C, from the common standpoint, point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. That is to say, CF equals to CD. Again, CF equals to CD according to rule number 2. Likewise, if we focus on the common standpoint, point B, from the common standpoint, point B, we have two tangents to this circle, tangent BD and tangent BE. According to rule number 2, they are equal to each other. That is to say, BE equals to BD. BE equals to BD, also according to the same rule number 2. Then we join points O and B together by straight line. And we join points O and C together by straight line. Here we created those two right triangles. In the next step we proved that the yellow right triangle EOB is congruent to the yellow green triangle, to the green right triangle OBD. So why those two right triangles congruent to each other? First of all, EB equals to BD according to rule number 2. E equals to ED according to rule number 2. In addition, those two sides are both the radii of this circle, therefore they are equal to each other. And finally, BO is a common side that belongs to both triangles, so I can write down that BO equals to itself as a common side that belongs to both triangles. So I shall prove that all the three sides of the yellow triangle EOB are correspondingly equal to all the three sides of the green triangle BOD. Therefore, those two triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. Repeat again. So if we define one angle as theta, then the other angle must be also equal to theta. So theta plus theta equals to 60 degrees. That is to say, 2 theta equals to 60 degrees. We divided this equation by 2 and finally found out that theta equals to 60 over 2, that is 30 degrees. So this is angle theta, that is equal to 30 degrees in size. Then I copied the right green triangle ODB in a new page and we analyze this right triangle ODB. This is the right triangle ODB that I copied from the original drawing. Side OD is the radius of the circle, therefore it is equal to R, and this angle equals to 90 degrees, it is angle theta. So this angle equals to 30 degrees, it is angle theta. So here, in the right triangle ODB, triangle 30 degrees equals to OD over BD. Triangle 30 degrees equals to OD over BD. OD is the radius of the circle, that is to say it is equals to R over BD. So triangle 30 degrees equals to R over BD. Then we multiply this equation by BD, and then we divide it by triangle 30 degrees, and finally we found out that BD equals to R over triangle 30 degrees. This line segment BD equals to R over triangle 30 degrees. Then we repeat it on the same process on the orange and the pink triangle. we actually proved that those two right angles can go into each other according to side rule. Again, why those two right angles can go into each other? First of all, CF equals to CD. CF equals to CD according to rule number 2. In addition, those two sides, they're both the radii of this circle, therefore they are equal to each other. And finally, CO is a common side that belongs to both triangles, so we can write down that CO equals to itself as a common side that belongs to both triangles. So I actually proved that those two right angles can go into each other according to side rule. And from the fact that those two right angles can go into each other, we will derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 75 degrees. Okay, alpha plus alpha equals to 75 degrees. That is to say, 2 alpha equals to 75 degrees. We divide this equation by 2 and finally found out that angle alpha equals to 37.5 degrees. This is angle alpha. This equals to 37.5 degrees in its size. Then I copied the orange triangle ODC. This is the orange triangle ODC. In a new page, and we analyze this orange triangle ODC. So actually, this is the orange triangle ODC that I copied from the original domain. Side OD is the radius of the circle that is equal to R. We just write down found out that this angle equals to 37.5 degrees. It is angle alpha. So in this right triangle ODC, times 37.5 degrees equals to OD over DC. Again, times 37.5 degrees equals to OD over DC. OD is R, so it is R over DC. So in conclusion found out that times 37.5 degrees equals to R over DC. Then we multiplied this equation by DC and then we divided it by times 37.5 degrees. And finally we found out that DC equals to R over times 37.5 degrees. Here, this is line segment DC that is equal to R over times 37.5 degrees. Okay, and from the drawing, it is very easy to see that side BC equals to BD plus DC. Again, BC equals to BD plus DC. BC equals to BD plus DC. Again, BC equals to BD plus DC. So BC is 2 according to what is given as the question. BC is 2. BD, we have already found out that BD equals to R over times 30 degrees. Here, BD equals to R over times 30 degrees. Plus DC. DC, we just write down found out that DC equals to R over times 37.5 degrees. So in conclusion found out that 2 equals to R over times 30 degrees plus R over times 37.5 degrees. Here we took R a second factor out of those two expressions. So 2 equals to R, R was taken as a second factor. So inside the brackets we left only with 1 over times 30 degrees from this expression, and from this expression we left only with 1 over times 37.5 degrees. So in conclusion found out that times 2 equals to R plus 1 over times 30 degrees plus 1 over times 37.5 degrees. 1 over times 30 degrees equals to 1.732. And 1 over times 37.5 degrees equals to 1.3032. So in conclusion found out that 2 equals to R times 1.732 plus 1.3032. 1.732 plus 1.3032 equals to 3.0352. So in conclusion found out that 2 equals to R times 30352. We divided this equation by 30352 and found out that R equals to over 30352. That is actually 0.6589 units, and this is actually the radius of this circle that is inscribed by triangle ABC. Repeat again, in both methods we actually found out that the radius of this circle that is inscribed by triangle ABC is equal to 0.6589 units. Okay, thank you very much.